Okay, so today we're going to talk about electric potential. So we're going to talk about relating electric potential to field, sources of electric potential, conductors, and capacitors. So we talked a little bit about this in the last chapter about equipotential lines. And so these lines are, in this picture, are the green lines. So the green dashed lines here represent lines of equipotential, and they are lines that connect points in space that have the same potential, so the same electrical potential. And notice too that here we also have drawn electric field lines. So my electric field lines are pointing from a positive to a negative, right? In the middle, they point straight from positive to negative. So these electric field lines are they are showing you the locations in space where the electric field is the same. And notice that the equipotential lines, the green lines, are perpendicular to the electric field lines. So this is an example of two charges, and this is a 2D representation, but realize that this is happening in all space. So you could imagine that the field lines are coming out of the page, right, and going into the page. And the potential lines are wrapping around out of the page and into the page. In this example, this is a 1D or 2D example where our electric field points from the positive plate to the negative plate. So this is, imagine these plates extend into the page and out of the page. And my electric field points to the right from positive to negative. And the equipotential lines, meaning the lines that where in space where the potential is the same, are perpendicular again to the electric field. And you can see that my voltage for these two plates go from 0 volts to 5 volts, 10 volts, 15, 20 volts. So it's changing by 5 volts, and it looks like it's pretty, the spacing's equal. So I'm having a linear change in potential as I go from a negative to a positive, and just notice my electric field lines are pointing from positive to negative. So what about connecting electric potential and electric field? This is a nice slide that kind of shows you the 4 key ideas. Notice that the force and the potential energy, so U is the potential energy, the force acts locally, right? So I have charges, and if I think about one charge, there's a force acting on that charge due to the other charges. And the same thing for energy. If I have a bunch of charges and I think about one of the charges, one of those charges has potential energy due to the potential of the other charges. So this is on the left side is our force concept. So notice the force and the electric field both are vectors. Where on the right side, the potential energy and the potential are energy concepts. Notice that the electric field, right, it's everywhere in space. So if there is charge, there is an electric field. Just like if there is a mass, like the Earth has mass, so therefore there is gravity. And there's also the electric potential. So if there is charge, there's going to be electric potential. And then notice for the energy concept, just like energy when we were talking about forces and energy, that our energy is a scalar, right? So the potential energy and the potential are scalars, whereas for the force, when we talk about force and field, those are vectors. So if we want to talk about how we relate potential and potential energy, right, we have a collection of source charges, and so they have a potential energy. The system has a potential energy, and if I want to find the potential in space, I just divide by charge Q. So that if I think about the equation, my potential energy is KQQ over R squared. Sorry, KQQ over R, whereas my potential is just KQ over R. So I'm just dividing the potential energy by a charge to get the potential. To calculate potential energy is defined in terms of the work done by a force on a charge as it moves from position I to position F. So that's just rewritten as the change in potential energy is a negative of the work from I to F. And so I can write that as a negative of the integral of the force times the distance, or the distance it travels, right? And so when I look at this becomes my dot product, right? So I'm looking at the force in the direction of the change in position. So, and also remember that the force exerted on a charge Q by the electric field is F is equal to Q times E. So if we put these together, right? We were starting here, my delta U. If I want to calculate V, I know that V is equal to delta U over Q. So that means that I'm going to have my delta U is equal to the final potential minus the initial potential. And if I substitute in here, this is equal to QE, right? But I'm dividing by Q, so I just get E here. So I'm going to have E ds, and so going from initial to final position, I'm going to have a negative E ds. So if I just look at this example, so here is my source charge, negative charge, and I have a charge here, and I'm just showing that if I have this charge and it has a velocity, so this is representing velocity, it feels a force to the left, and as it moves to the right, it's slowing down, and it feels a stronger force. And so that's where the negative comes in. So I can see that my negative, I've got this this field that my charge feels, and it's getting weaker, and it's also pointing to the left. So that's where I have E dot ds is going to be negative. So I have a negative times a negative, and I'm going to end up with a positive value for my delta V. So to calculate the potential from the field, right, I have the same equation, delta V is equal to V final minus V initial, and that's equal to a negative of the integral from the starting position to the final position of the field that the component of the field that's in the same direction as the change in position. And how do I go about calculating the potential from the field? So some good problem solving strategies are to draw the picture, of course, identify the point at which we want to find the potential. So mark that as P, or call it position F. Choose the 0 point of the potential. And when we deal with charges, this is often at infinity, and call this position I. And then establish a coordinate axis from I to F. And then carry out the integration. So then go through and do this integral. Okay, in this example, we need to find the potential given this electric field in the graph. So we see that the electric field in the x direction is linear, and we need to figure out the potential, and we need to draw a graph of it, and we know that V equals 0 at x equals 0. Okay, so we're going to use this equation. Let's change the drawing. So V is equal to a negative E dotted with ds. And when we have an integral like this, if we have a graph, then the integral is just the area under the graph. So we're just adding up all the pieces underneath that line that represents the electric field. So this is going to be area under the graph. So V then is equal to 1/2 for that triangle, base times height. So V is equal to, and I forgot my negative, so a negative 1/2. So the base here, along here, is going to be x, right? So that base is x. And then the height, when I think about that, all along here, right, is the height. And so that height is represented by the line. And so that's 1000 x. And so when I multiply that together, I just get V is equal to a negative 500 x squared. And x squared is just a parabola. I could also do this using the integral. So if I want to use the integral, I see that my E is a line represented by the slope. So think about the line as y is equal to mx plus b. So let's just write that. So if y equals mx plus b, if I'm plugging that in, right, my E is the y, so I'm going to have E. The slope is, if I look here, the slope is just 100 high and by 1 here. So I'm just going to say, or sorry, 1,000. So 1,000 over 1, that's my slope. And my x is just x, and I don't have a b, so the b goes to 0. So on my E is just 1000x. So I can write that, if I want to just do this the other way, V is equal to a negative. My E is 1000x, and my ds is just dx. Okay, so that means I'm going to have V is equal to, I can take the 1000 outside of the integral, and then I have x dx. So if I do that integral, I'm going to have a negative 1,000. And then x dx, when I take the integral, is just x squared over 2. So v then is equal to a negative 500 x squared. Same answer. Now I need to graph it. So my graph is going to be v here, x and v. And I know I start at x equals 0, so I'm going to have something that looks like this, right, like a parabola. And so we can plug in our values here. So let's say at x equals 1, I'm going to have, say this is going to be, this is 1, I'll say this is like 500, negative 500. As when I plug in x equals 2, then I'm going to have 4 times 500, which is like 2,000. So maybe I should make my 1 a little bigger, or my 2 a little bigger. Let's say that's my 2. 2. And so this is going to be like there, like that's 2,000. And then it's just going to go and get bigger and bigger in the negative direction. Okay, so in this problem, we're using the fact that the electric field inside a capacitor was found to be E is equal to Q over epsilon naught times A from positive to negative. And we are asked to find the electric potential inside the capacitor, and we need to let the potential equal 0 volts at the negative plate. So let's draw our capacitor. So we'll make this negative, and we'll make this positive. And it says from positive to negative, which of course we know, right? So this is going to point this way. And notice that Q over epsilon naught A is a constant value. So that just means my arrows are the same length. So that's how I'm representing it, that they have the same length, so they have the same magnitude. And let's say that, so this is 0 volts, and this is some other voltage we don't know yet. That's what we're solving for. We'll say V final. Let's say we're solving for V final. And let's say this is x equals 0. And then let's say that this is going to equal x equals d. Okay, so our equation that we're going to use is V is equal to V final. And that's going to equal the initial potential minus E dotted with ds. Okay, so in our example, we know that the initial voltage or the initial potential is going to be 0. So that's going to go to 0. So we're going to have V is equal to a negative E dotted with ds. So V is equal to a negative. Now E is pointing to the left. So that tells me that that my E is actually a negative Q over epsilon naught times A. Right, and why is that? Because, so I'm saying that the positive direction is to the right. All right, so that's positive x. So my E is to the left, so that's where the negative comes in, and then my ds is really dx. And I'm evaluating this from 0 to d. Okay, so plugging that in, then I get V is equal to a negative times a negative is a positive, and my Q over epsilon naught times A, and I just have the integral dx from 0 to d. And so the integral of dx is just d. So I get V is equal to Q over epsilon naught times A times x, right, evaluated from 0 to d. So that just becomes V is equal to Q over epsilon naught A times D. Oops. What happened? Let me see if I should use the erasers so it doesn't do that again. Times D. Yep, and that's so that's my answer. And notice then I can just plug back in if I want to. I know that Q over epsilon naught A is just E, so this becomes V is equal to E times D. And D can be in any direction, so I could make that S if I wanted to. But basically, it's the electric field, the magnitude of the electric field times the distance between the plates. So here we have two plates, and the two plates have a potential because there's a positive plate and a negative plate. And I can see the potential at the positive plate is 20 volts, and at the negative plate is 0 volts. And if I didn't know anything about the electric field, I can calculate it just from that information. So the equation to find the electric field given a potential is negative dV ds. So I just take the derivative. I also know that the potential is linear. So I know that it changes linearly, meaning if I were to have a graph, it would look like y equals mx plus b. So it's linear. So if it's linear like that, then I can use the equation a negative delta V over delta S. So so just looking at that, I forgot my negative here. There should be a negative outside of here. So my E would be delta V over delta S. So my delta V, if I'm going from left to right, I end, my final is 0 volts here, and my initial is 20 volts. So I have 0 minus 20 volts. And then as I'm going from left to right, I'm starting at 0 and ending at 0.01. So I have the final is 0.01 minus 0. So I end up with a positive on the denominator, a negative in the numerator, but then I add in this negative value here, this negative sign here, and I end up with a positive electric field. And so that's just telling me that the field is pointing in the positive x direction. So that would be how you'd calculate the electric field for two plates with charge on each one that creates a charge separation. Okay, in this problem, we're given the slope. We're given the graph of the potential versus position. And what we need to do is we need to find the electric field, and the electric field is given by the slope. It's dV dx of the potential. So I'm going to say that E is equal to a negative dV dx. And we know that it's a vector, right? So this is in the I direction because I'm only given the potential in terms of x, so I don't know if there's anything. I'm going to assume it's 0 for the j and the k directions, or the y and the z directions. Okay, so since I know this, E is just the slope, a negative of the slope. So if I look at the slope right here if I look at this slope right here, that slope is positive, right? It's changing, it's increasing in the y value. The potential is increasing over the range. So its slope is 10 minus a negative 10 over 2 centimeters. So I'm going to break this up into 3 sections. So let's call this section 1. This is 2, and this is 3. Okay, so E1, we'll call it E1, is equal to a negative of, so I'm going to call like 10 final and negative 10 initial. So I'm going to say 10 final. Now let's do this before we do that. Let's say this is negative delta V over delta X, since it's linear. So that's going to equal a negative 10 volts minus a negative 10 volts all over 0.02 meters. And if I work that out, that tells me that E1 is equal to, so 10 minus a negative 10 is a negative 20. So I'm going to have a negative, so this is 10 plus 10. So that gives me 20, negative 20 over 0.02 meters, volts, and that's going to equal 1,000 volts per meter. So that's for area 1, that's the electric field. And now for the electric field in area 2, right, my slope here it's a horizontal line, so my slope is actually equal to 0. So E2 is equal to 0 because of that horizontal line. And then what about E3? So E3, oops, let's move that up and draw, and I'll erase my 3 and make that a little better. So E3 is again going to be a negative of delta V over delta X. And then when I look back, this is a negative slope, so I'm finishing at, that looks like maybe 5? I think it still ends at 10, so that still looks like it's a 10. Okay, so it's ending at negative 10, and it's starting at positive 10. So I'm going to have a negative. Switch to drawing a negative of a negative 10 minus 10. These are both volts over 0.04 meters, right? Because in this case, we're going from 4 to 8. So the range is 8 minus 4, which is 4 centimeters or 0.04 meters. Okay, so I got that. All right, so here then E3 is going to be, so I've got 10 volts, negative 10 volts minus 10 volts gives me, this is a negative 20 volts. But I have a negative out front, so I'm going to get a positive 20 volts over 0.04. And so that's going to give me 500 volts per meter. So if I want to draw that, draw the graph, this is going to be my E, and this is going to be my X. So from, let's see, 0 to 2, let's make this 2, this 4, and make, I guess I'm going to add a little more, oops, undo, just erase the X. A little farther out, so maybe make that 8, and this is X in centimeters. Okay, so I have negative 1,000 volts per meter. So I'm down here for the first 2, then I go to 0 from 2 to 4, and then I'm at about 500 volts per meter. So I'm here. There we go. Okay, so you can see that graph now for the electric field, and we can see that the electric field is the, again, just to go over that again, is the slope of the potential. So if I look at the slope of the potential, my slope is a constant in area 1, it's 0 in area 2, and the slope is negative in area 3. And so my electric field is negative of the slope, so that's why the electric field switched sign compared to the potential. Well, what about when we talk about the electric potential for 2 dimensions or 3 dimensions? When we want to do this calculation, we need to determine the slope in each direction. So this is an example of 1D, right? We would only have my potential is changing just in the x direction. So I would not have the j or the k components for calculating the electric field. I would just use this first term. Whereas if I had this case, this is a 3-dimensional example. I have the electric field that is coming out of the page. It's going to the right. It's going into the page. And so here I'm going to need to calculate each one of these derivatives in the I direction, the j direction, and the k direction. And my electric field will have the I, j, and k components. So in this case, my E is just going to have the I component, just this term. In this case, I'm going to have all 3 terms. So what about electric field in conductors? Well, we know that the electric field inside a conductor is 0 when all the charges are at rest. And any net charge on a conductor is located on the surface of the conductor. So, and the electric field is always perpendicular to the outside of a conductor. So just thinking about that a little bit more, here is my conductor. So I have a thick shell, a thick conductor, and so inside this conductor, inside here, my electric field is 0. Inside here, in this space, there is an electric field because there's this charge, and if we thought about Gauss's law and drew a Gaussian surface, right, I would have flux going through my Gaussian surface due to this charge. So here I have a field. And what happens is the charges are free to move in a conductor. So all of the negative charges move to the left because they're attracted by this positive charge, and this happens instantaneously. They move to the inside surface of the shell, and that means there's a net positive charge on the outside surface of the shell here. And so in between, we end up with an electric field of 0. So the charge is balanced, and inside here I have a net electric field of 0. And then just like we were talking about the electric field, so since charges can move, any initial electric field that is parallel to the surface, right, will cause electrons to move until the parallel component, this parallel component, is 0. So we'll always have an electric field that is perpendicular to the surface. Right here, I have an electric field that's perpendicular to the surface. Inside here, my electric field is perpendicular to the surface. So that's true of conductors, and that's due to the fact that electrons are free to move, and they move instantaneously in reaction to a present field. So another example of conductors is electric shielding. So if I have this little cavity inside of here, so I have a conductor with a cavity inside and no charges inside here, and I place 2 plates, a positive plate and a negative plate. I place this this shell inside in between them. This here creates this field. So I get an electric field from positive to negative. And I get a field here from positive to negative, from positive to negative. And notice that the charges move so that the negative charges are attracted to the positive plate, and the positive charges are attracted to the negative plate. But inside of here, the electric field is 0. And inside of here, the electric field is 0. And so a great example of that is a Faraday cage. And so this is an example from the Boston Museum of Science where these are Van de Graaff generators. And so Van de Graaff generators are creating a potential and creating a field. And so here we have this is a bird cage. And so these are metal wires, and there's a person inside of there. I don't know if you can see them. And that person, the electric field lines are going from the domes of the Van de Graaff generator to the outside of the shell, but the person inside is safe. And that's because they're inside this cavity, right? And there's no electric field in here. And if you notice, they're even holding on right here. And so they're even touching the inside. So they're touching the inside of here, imagine, and they're still safe because there's no electric field. So any separation of charge creates an electric field, and any separation of charge also creates a potential difference. So in this example, we have positive charge here, negative charge here, and that creates an electric field, and it creates this delta V, this potential difference. And Van de Graaff generator, which we've seen demonstrated in class, just to go through how it works, I have this motor, and this motor is rotating, and there's a belt connected, and so it's making this belt go around and around and around. There's a corona discharge here on this needle, and that is giving off positive charges. And the positive charges, it's this needle is really, really close to the belt, and so those positive charges are coming up the belt and coming around, and then there's another needle here, like a pointed wire, and that's collecting this positive charge, which is collected to the hollow metal sphere, and that's what's charging the top of the Van de Graaff generator. Let's talk about capacitance. So a capacitor stores electric charge. So you can see here a capacitor is just 2 plates that have a separation between them, and they can be connected by these wires to a source of potential. So a battery, a power supply, something like that. Notice the A represents the area of that sheet, right? So that's just going to be the area of a rectangle. And D is the separation between the plates. And so the way a capacitor is made typically is we have these sheets. Imagine these are sheets of like aluminum foil, and we put some sort of insulator in between them and we stack them. And so we have stacks of aluminum foil, insulator, aluminum foil, insulator, aluminum foil, insulator, and then we roll them up. So we roll them up into a cylinder, and then we place them into a can. And so these are some examples of capacitors. So here's like the can, and this size of this one is about like a Coke can, maybe a little bit smaller. These are smaller. This one's kind of like, think the diameter is maybe the diameter of a pen, and then these are super tiny, super tiny, like a little tiny piece of candy or something like that. And this is called a Leyden jar. So this is an early example of a capacitor. Another example is electrophorus, which we sometimes do a lab with an electrophorus plates. But just as an example of what's inside a capacitor, right? So we've got, this is what it looks like on the outside, but if you open it up and look inside, we have these metal sheets, right? And then these sheets of dielectric or insulator inside a can, right? We close them up, and then we have a positive connection and a negative or a positive connection and a negative connection. So that's just, if you were to open it up, that's what it would look like inside. When we want to create a diagram, right? This is a wiring diagram. This is a circuit diagram. Notice my two plates, right? And my battery here. And my battery, this is the plus side, and it's connected to the positive side here. Negative side's connected to the negative side here. So you can see that my battery is a source of potential. And then when it's connected to a battery, my capacitor is a source of potential. Notice the difference between the electric symbols used for a capacitor component. The lines here are the same size, whereas for a battery, the positive side is represented with a longer line here, and the shorter side represents the negative side. So some properties of capacitors. Capacitance, the equation, we can represent the total charge in a capacitor is equal to the capacitance C times the potential. And so the unit of capacitance is the farad. And so if we just take and rewrite this equation, C is equal to Q over V. And so the units of charge, Q, are coulombs, and the units of potential are the volt. So that's where we get the farad is a coulomb per volt. Capacitance depends on size, shape, relative position of the plate, so the D, the separation between the plates, and the material that separates them. So this insulator, what properties does it have? And that contributes to the capacitance. So the equation, the capacitance is equal to the permittivity of free space. So when we say the permittivity of free space in this example, for this equation, we're assuming then there's no insulator. Air is acting as the insulator. And A is the surface area of the plate, so the area of the rectangle, and the separation between the plates. So capacitance is equal to epsilon naught times the area over the separation. So dielectrics are what make up the insulating material. So examples are paper, plastic, glass, or wax. And these sheets of this are placed between sheets of metal to create the capacitor. And the purpose of the dielectric, or the insulating material, is to allow a higher voltage on the capacitor because they make it more difficult for charge to flow, and the plates can be closer. And that's good because if we look back at the equation, if my plates are closer, that means D is smaller, and that means capacitance can be bigger. So dielectrics, for a capacitor with a dielectric, the capacitance becomes epsilon A over D. And so this epsilon is just K, the dielectric constant, times epsilon naught, the permittivity of free space. And epsilon is called the permittivity of the material. So when we just have epsilon naught here, we don't have a dielectric material in the capacitor, and we almost never don't have an insulator. So our capacitance is just epsilon times A over D. And you can see here just another example. So this is my connecting wire that's going to go to, say, a battery or power supply. And this is maybe the negative side, my two plates, and then my dielectric. When we put capacitors into a circuit, we can think about them as in series or in parallel. And so when we draw capacitors in parallel, right, we draw them in a circuit diagram like this. Notice my battery, right? So this is the positive side of the battery. And notice it's connected over here to the positive side of each of these capacitors. And the negative side of the battery is connected to the negative side of each of these capacitors. Notice each of the capacitors has a Q. So that's the charge held by each of the capacitors, and each one can have a different Q. And when I add up, when I have capacitors in parallel, all my Q's add. So Q1 plus Q2 plus Q3. So when I add them up, Q1 is just C1, the capacitance times the voltage, C plus C2 times the voltage plus C3 times the voltage. The voltage is the same for each of these because notice that each of the capacitors is connected to the same voltage, right? The same battery. So if my battery is 1.5 volts, then the voltage across this capacitor is 1.5 volts, same here, 1.5 volts, same here, 1.5 volts. So if I rewrite this equation, I can factor out the potential right here, and I'm left with the addition of the capacitors. So the capacitance. So C equivalent, if I were to redraw this circuit, I could represent all of these by just one capacitor, and I would calculate that capacitance of that capacitor as C1 plus C2 plus C3. For capacitors in series, we draw them like this. And again, each of these capacitors has a charge Q. And for capacitors in series, we have a voltage drop across each of the capacitors. So it's kind of like we add up the voltages for each of these to come up with the total voltage. So my voltages add, so Q over C1. So remember, I'm using this equation right here. So if I'm looking for voltage, I'm going to have Q over C. So that's where Q over C1 plus Q over C2 plus Q over C3. If I factor out the Q, then I'm going to have 1 over C1 plus 1 over C2 plus 1 over C3. And so when I redraw this circuit with just one capacitor representing all three of these, then I know that equivalent capacitance is going to be the reciprocal. So 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So what about stored electrical potential? So capacitors store electric potential energy, and so we can talk about that potential energy as we can use any one of these equations, 1/2 Q times V, so 1/2 the charge times the potential, 1/2 the capacitance times the potential squared, or 1/2 the charge squared over the capacitance. So you can use any of those equations. And that's all we have.